finally, we have approached section B. So let's try this now. So question 4. The 2011 Fukushima nuclear disaster raised questions about the wisdom of utilizing nuclear power. State two arguments for and 2 arguments against the use of nuclear fission reactors. Arguments for, so this is pretty simple. You either know it or you don't know it. There's no calculation involved. So electricity for consumers will be more affordable. Well, let's just say it will be cheaper. Let's go easy in the long run. Boom. And then number 2, no greenhouse gases are emitted. No greenhouse gases like CO2, CH4, so carbon dioxide, methane would be emitted into the atmosphere as products of the reaction. I wrote a lot. Anyway, so that would be 2 points because it's 4 marks. So 1 point, 1 point. Now let's go for the against. Against, to build a nuclear power station will be very costly. So to build a nuclear power station, would be very costly. So you know, the startup, the whole point is it's something like solar energy. When it comes to startup costs, it can cost a lot more money to put these things in place, but eventually the money you spend to put it in place will pay off, because then you'll pay less for the electricity that's running through your house, and that will take about 5 to 10 years, maybe let's say 7, but you're gonna see the benefits later on. And then another one is that if there is any natural disaster, there is a fear of radiation leaving the factory and affecting the environment. Now note well, my points don't have to be your points. You could go into your textbook and find out more points, but these are the points, these are my go-to points anytime these questions are asked. Your text, especially the text by the concise text that came out, I don't remember the author, but I think it's a Collins concise text that has it well listed, so you can go into your textbook and look up other things, and it's good to know because they like to come with these questions. So if there is any natural disaster, there is a fear of radiation leaving the factory and affecting the environment. Okay, cool. Now the next one says nuclear fusion is seen as the great energy hope of the future. State 2 advantages of nuclear fusion over nuclear fission. Well, nuclear fusion is what happens on the sun. That's why we have light. And that's all the little eruptions you see happening on the sun. That's the energy of the sun. And it uses hydrogen. It uses isotopes of hydrogen. And the only thing that comes off is hydrogen, which is harmless to the atmosphere. So, unlike fission, which requires a radioactive element like uranium to give off heavy metals, nuclear fusion uses only hydrogen to give off hydrogen or helium and energy. So clearly, fusion is really the great energy hope, because we don't want any more bad things getting out there into the environment to make it worse for our offspring if we do give the earth procreate, if we do procreate eventually. So the starting materials used are not radioactive, which is the hydrogen. And 2, the products produced are not heavy metals. Are greenhouse gases. How cool is that? So that's that. So that one, electricity for consumers will be cheaper in the long run. No greenhouse gases like carbon dioxide or methane gas will be emitted into the atmosphere as products of the reaction. Arguments against: to build a nuclear power station would be very costly. 2, if there's any natural disaster, there's a fear of radiation leaving the factory and affecting the environment. And you know, the radiation leaving the factory could lead to mutations in human cells. And you really don't want that. You don't want mutation to occur so fast that the outcome of it is unrecognizable. You want mutations to happen naturally and slowly. And so, in this one, the starting materials used are not radioactive. The products produced are not heavy metals or greenhouse gases. Yes, my hand is quite tired. It's starting to shake. Who cares? Alright, so moving on, it says, correctly complete the following nuclear fusion reactant. So when you see the word fusion, we think about things being added. And if you look up here, 2 plus 2 is equal to 4. So it says 3 max. So I'm just going to write down something, but in our head we know what to do. So 2 plus 2 is equal to 4, and 4 minus 1 will give us 3. So we're going to put 3 up here. So 3 plus 1 will give us 4. Just writing something. So what plus 1 must give us back 2? 1. And so if you look across, you see that this is an isotope. No, this is hydrogen, and this is an isotope of hydrogen, and there's also another isotope of hydrogen, which is 3. So we're going to just put back H here. And if you look at the whole question, you would see that you have an isotope of hydrogen here. So you just put it back there, and we're going to complete this. We're going to say 1 plus 1 equals to 2. Minus 1 must be equal to 1. And that should give us our 3 max. Comprende? C. Now, it says a commonly used fusion reaction is deuterium and tritium, and then we have it giving off helium. Right? If my isotopes serve me correct, if my memory serves me correct on the isotope names. But yeah, so we have hydrogen and hydrogen again, and then we have the helium. and then what's coming off is 1 neutron. And we have all the masses here in U. We're going to convert the masses to kilograms after we do what we have to do. So it says the mass of the reactants and products of this reaction are recorded in table 4 below. And the question follows that, yes, I have a teensy table. It says, using the information in table 4, calculate the energy release in the reaction. So the energy is equal to delta E equal delta M C squared. And so are we looking for this? This is what we're looking for. And we already have this, and we already know what this is. And they gave it to us down here. Did they give it? Oh yeah. Yay, so they gave it to us already. C is the speed of light. So we know that before we had 2 reactants, which was H2, which is this, and H3. And if you look down here, you see H2 and H3, and these are the masses, right? So we're going to write here before minus after is equal to delta M. So before we have 2,1H and 3,1H. See? And then after the products we have 2 helium, and we have 1 neutron. Mind, I gave you a big space, so you could be as great as you want to be. And what we're going to do now is write down the mass for 2,1H, which is 2.0141017 U, plus the one for 3 is 3.01604,927 U. So that's before, minus, in brackets, we're going to have 4.00260,325 plus, we have the neutron right there, 1.00866,492. And we could just write here now. So see, that's what I was writing while we were looking at the numbers. And then we're going to start to add them now. Yeah, the number's long, but best to use the long numbers. And then when you finish using the long numbers, guess what? You could round up in the end. But don't round up too early, because you don't want to have yourself. You don't want to be short. 2.01410,178. Yes, you have to be careful. Plus 3.01604,927. Okay, is that correct? That match back? 3.01604,927. Okay, great. Match back. Equal to, okay, 5.03. So I'm going to put it right here. So 5.03015105 minus, and I'll put in numbers now again for the next side. You can say 4.00260,325 plus 1.00866,492. And we get 5.01126817. And we can just minus and put back in the big numbers. We can say 5.03015,105 minus 5.011266817, and we end up with 0.1888288U. And now that we have that, we could just convert it to kilograms one time. So you see, if we did it for each number, what would have happened? We would have run into all sorts of calculations, this, that. So we know that 1 U is equal to 1.66 times 10 to the negative 27 kilograms. So therefore 5.011266817U, oh boy, I wrote the wrong thing, 0.1888288U is equal to X kilograms. So what you're going to do is just multiply them. So X will be equal to 0.1888288U times 1.66 times 10 to the negative 27 kilograms divided by 1U. I'm just doing this so that you could see where you're going correct and where you're going wrong, because you need to carry your units at all times. And that's what I tend to tell the students that I have, that you should always carry your units. Now I didn't get rid of the number, so what I'm going to do is just put multiply by 1.66 times 10 to the negative 27, and I got 3.13455,808 times 10 to the negative 29 kilograms. See? Because only kilograms left. So now you know you have your mass, and we found the difference. So this is our difference. So we know that delta M, so we can just put here, which is equal to delta M, because I don't want to write back that wrong number. So now to find delta E, so delta E, so if delta E is equal to delta MC squared, and we know what C is, we can just say 3.13455,808 times 10 to negative 29 kilograms times 3 times 10 to the 8 meters per second times 3 times 10 to the 8 meters per second. I know I could just put it in brackets and put a square root to the top, but what happens is that when you take the shortcut, you forget to square. So if it takes you 2 minutes to just write it out, do it, because when you start to speed up your work, you know, you're gonna get it wrong. We all know you have to pace yourself, so always tell yourself each question you're gonna use 20 minutes to answer it, and you give yourself time. Okay, so I kept the number in my calculator again because I know I have to use it again, and I'm gonna do this time 3 times 10 to the 8 times 3 times 10 to the 8. Right, so that gave me 2.8 8 times 10 to the negative 12 joules, or K G m squared over s squared, which is, as I said earlier, equivalent to a joule. So now you know what the E stands for in your calculator. It stands for times 10. So don't write back 2.8 E negative 12. Just write times 10. Okay? And so I hope this works for you. I hope you got this answer. I hope you see that you can do it in less time. So again, what I did, I put down all of my before reactants. So anything before is reactants, and I put down the after, which is the products. And I minus 1 from the other. I got an answer. I converted it to kilograms because we need kilograms whenever you're dealing with E equal mc squared. Mass must be in kilograms. And then from doing that, I stuck it in the equation and I got 2.8 times 10 to the negative 12 joules. Yay! Good luck!